Okay, so taking a look at quiz number 3 from 2014, number 5. The question states, how many possible stereoisomers are there for the following compound? So the first thing you want to do, right, is usually the equation is 2 to the n, where n is equal to the number of stereo centers, asymmetric centers, chiral centers, where n is equal to the number of chiral centers. So that means sp3 hybridized bond to 4 different things. Right? So in this case, you actually should see that there are 2. Right? Because there's a hydrogen that's implied here, right? But you should know that. So each one of these carbons is sp3 hybridized and bonded to 4 different things. Now some would say, well, this is a CH2 and that's a CH2, but they're not the same CH2, right? In a carbon-13 NMR, they would have different peaks, right? They're not the same CH2. Now the trick here is, normally you say 2 to the n, right, where n in this case would be 1, 2. So you'd say, oh, there's 4 stereoisomers. That's not the case here because this molecule has some symmetry, right? If you look at this molecule has some symmetry, right, down the middle. What's that going to cause is that one of these, you're going to have less stereoisomers than you'd expect, right? You're going to have less stereoisomers than you expect because there's going to be, one of these stereoisomers is not going to be, they're going to be meso. There's going to be 2 meso compounds, and they're going to be exactly the same then. So let's just take a look at what this could possibly be. So let's shrink that down. The way to know this, you got to actually draw in the wedges and hatches. Now if you look at this is one possibility, right? This chlorine could be wedged, and this chlorine could be wedged. But when it's this way, look at this molecule. Does this molecule have a mirror plane? It does. So this is a chiral or achiral molecule? Achiral. If you have a mirror plane, you are achiral. Even though it has chiral centers, right? The molecule's chirality is not always predicated on whether or not it has chiral centers. So this molecule is achiral, and it's not just achiral, it's achiral and it's meso. Now what that means is, what if I drew this same molecule, or well, it's not going to be different. What if I drew it with the hatches? What if I made the chlorines going away from us? If I drew this one, what's the relationship between this molecule and this molecule? They're not enantiomers. They're exactly the same. If you take this and flip it on its head, it looks just like this, right? So these 2 compounds are exactly identical. They're both meso, but they're identical.
And if we did it without rotating, we would just find R and S and then see that they're the same.
You do R and S and see that they're the same. Right? But they're identical, right? They're identical. It actually has nothing to do with So they're exactly the same. And then the other ones, right, you can have different, right, this wedge and this hatched, and then this wedge and hatched, that gets you there. So you actually don't have 4 in this case because 2 of the ones you would draw, right, if you had to draw these out, this would be one I draw, this would be the other one I draw, and then there's 2 more with, right, flipping spots. Since these are the same, I don't have 4 stereoisomers. In this case, I actually only have 3. So the equation doesn't quite work when you have meso possibilities. So you got to be careful. So if we were to rank these R and S, let's do that quick. So this would be red, H would be green, and here we have a carbon to carbon, that's a tie, CH2, 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 tie, CH2, carbon with the chlorine, this side wins. So this would be white, and this would be blue. So the carbon I have starred here as carbon 1. Where is carbon 1 at in this molecule? It's actually over here. It's opposite side because it flips over. So they're identical. Good. Okay, so this is an example. It's from the PowerPoints. I want to say it's from the PowerPoints on 1028. It's slide 10. 1028, slide 10. It's also discussed quite a bit in Top Hat on page, hold on one second. So it's also discussed in Top Hat in section 6.3 and 6.4. There's also quite a bit of good questions in Top Hat in Chapter 6, stereo question, homework questions about identifying chiral and achiral molecules. So check out homework questions in Chapter 6, stereochemistry homework questions. Something like 6.1 I'm looking at right now would be a good one to look at too. But for these kind of things, you need to recognize, does the molecule have an internal mirror plane? So in this case, if you split it down the middle here, right, it would be, if you folded this on itself, right, it would fold up and be identical. Now if you fold it this way, it wouldn't be identical, but you just need one mirror plane. Now the moment you add something out here, it's gone, right? Once I add some sort of side chain anywhere, it's gone, right? So be careful where that's at. So if I was an internal mirror plane, right, internal mirror plane. Incidentally, if I erase, let's see if I can, no, it's not gonna let me, pretend this is not here. Does this molecule have any asymmetric chiral centers?
No.
If I got rid of that? No, it doesn't, right? So yes, there are, right, there's an H here that's going away from us, but is this carbon different than this carbon if this isn't here? These are exactly the same, right? So it's not meso either. It's just achiral, right? Remember, meso is achiral with chiral centers. This is just an achiral molecule. This doesn't have asymmetric centers. All right, so then if I drew something similar, if I put a CH3 here, and then put that OH maybe wedged over here. Now this is achiral. Now there's no longer a mirror, there's no internal mirror plane anymore. So now this is a chiral, this is a chiral molecule. This is achiral, this is chiral. All right, taking a look at quiz 3, 2014, number 4, the second one, B. So this is in a ring, but that doesn't mean we still can't do E or Z, right? So the rules all still apply. You split the alkene in half, that's the first thing we do. And we look at each individual alkene of the carbon and what they're bonded to rank them, right? So from this side, we go to carbon, that's a tie. And we say, what is this carbon bonded to? It's bonded to a carbon and 2 H's. And what is this carbon bonded to? 3 H's. So who wins? The top one does. So the star would be over here. Go to here on this side. We go to carbon, that's a tie. What is this carbon bonded to? An oxygen, a carbon, and an H, right? Or you play your high cards. What is this carbon bonded to? Oxygen, and oxygen. So who wins? This one does. So are the stars on the same side or opposite sides?
Opposite.
So it's not Z same side, it's E.
We don't have an oxygen.
So if you're having trouble seeing this, one thing to do, you could say, well, this is A. This is one bond out. That's A. Right? This would be B. Here for this one, B would be an H, 2 bonds out. Right? So you want to find that differentiation. So you compare A to A. They're both carbons. Then I say, what is A bonded to? A in this case is bonded to a carbon and then 2 hydrogens, which are not drawn in. This carbon is bonded to what? 3 hydrogens. Right? So who has a higher priority? Carbon beats hydrogen, so this has a higher priority. All right, so naming alkene. So the first thing you need to do is find the parent chain, and the parent chain must contain the pi bond. So in this case, the parent chain, I'm going to circle it, is this, right? So it's a cyclohexene, right? Cyclohexene. And the way you want, why? So cyclohex, right? And has a pi bond. One, it's an alkene, so it's it's cyclohexene. That's right, sp2. Good. Now the question here is, how do we number this? All right, there's 2 choices, right? We can either number it going 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Right? The best way we're going to number it is clockwise. Now, why is that? Is because if I make this carbon 1, then I also have a 1-methyl, which would be the lowest number for the first group. If I numbered here, I'd have 2-methyl, which would be higher than 1. Right? So I'd rather number it this way, so it's 1, 2, 3, 4, 5, 6. Because I want to have, remember, when you do rankings, it's not about having the lowest number total for the substituents, it's having the lowest number substituent first. Always have the first one low, right? So I want this to be lowest because the group off of my parent chain would have the lowest number this way. So how do I name it? It will be cyclohexene. Now you can put a 1 in front if you want. Sampling won't like that, but that's fine, right? Now what else the groups are off of this? We have, looks like we have 5-chloro
1,4-dimethyl.
and a 1,4-dimethyl.
And then that's already alphabetical.
And it's already in alphabetical order, so it would be 5-chloro, 1,4-dimethyl, cyclohexene, or 1-cyclohexene. Either way is fine. Right? So you want to have, again, find the parent chain with the pi bond in it, and you want to have the lowest number possible for the substituents off of the parent chain. So trying some resonance questions. So this is from our resonance workshop from 9/14/16. It's in your class notes. It's also in, there's a resonance structures key as well. So going through these practice ones. So the way to think about this one, right, we're moving electrons. If I look at this, right, the easy one maybe to do right at the bat is move these electrons here, which is then going to break that pi bond, right? We're moving 2 electrons at a time, double-headed arrow, resonance arrow. O minus.
I don't know why we started.
Right, I'm just showing one possibility. We always balance our charge. So that's one thing you could do. That's not enough, though. That's kind of the easiest one to see. Now, if you look at something like this, right, you should look at that N, and that N has what charge? Plus. And it has a full octet, but these oxygens probably pull electron density, right? And they might even pull electron density out of this ring. Right? When we think about resonance structures, we're thinking about a p orbital system, right? All these have p orbitals. So they're either sp2 or sp hybridized. They all have p orbitals. They're all lined up, right? All these p orbitals are lined up. So we can move electrons through that, right? So what can we move in resonance structures? We can move lone pairs. So in this one, we move lone pairs, right? There's lone pairs we moved here.
Where's the lone pair for that one?
They're implied there. I didn't draw them in, but they're implied. If you see an oxygen with a negative charge, you automatically know oxygen has how many lone pairs? 3. You should automatically know that. Right? That's unit 1 stuff. If you see a nitrogen with a plus charge, how many lone pairs does it have? 0. But it still has a full octet, so it's fine. But it's electron deficient, right? These oxygens are pulling on it. So maybe we should push some electrons towards that nitrogen. Right? Push some electrons towards that nitrogen. So let's do that. Right? Let's break this pi bond. Right? And notice things have to be next to each other. This sp2 hybridized carbon must be next to whatever we're moving it towards. Right? You can't have a break in the p orbital system. Everything has to be sp2 at least lined up next to each other. Everything must have a pi bond or a p orbital lined up next to each other. So as I do that, if I make that bond, I must break that bond. Resonance arrow, double-headed. So now, one thing I could do, let's number these carbons. 1, 2, 3, 4, 5, 6. Which carbon lost electrons? 3. So where should there be a plus charge? At carbon 3. Who got electrons? Who actually ended up with the electrons? Look how they, right? Electrons flow. Notice also, electrons flow in one direction. They don't come back around. They flow toward the oxygen, which makes sense. Is oxygen electronegative? Yeah. Let's give oxygen electrons. So there'd be a plus charge here. There'd be a new pi bond between carbon 2 and nitrogen. Right, now there's a negative charge on that oxygen. How many lone pairs does this oxygen have here? Lone pairs it had 2. Now how many does it have? 3. I didn't draw them in, but you should know it. You should know they're there.
Would that nitrogen still have a positive?
This nitrogen should absolutely still have a positive charge because when you do resonance structures, you always must balance your charges. Right? What was the net overall charge to start? 0. So if I make a plus charge, I better make a minus charge too to balance the charge out in this case. All right, do our numbers. 1, 2, 3, 4, 5, 6. So I can keep doing resonance structures.
Why is this
How
N
many
staying
possible
positive?
does it have?
How many are possible? I don't know.
How many do you want us to do on the quiz?
I would tell you how many I want.
Is it gonna look something like this, or is it gonna get more complicated?
I mean, I mean,
I could do
Just
this.
answer.
I don't know. Yeah, right. I can't. I mean, it's not gonna get more. I mean, I don't know how I could make it more complicated
Make a big sigma.
necessarily.
Maybe like switching charges or something.
But then you just balance your charge, right? So always keep the principles alive. You don't break sigma bonds, right? Don't break sigma bonds. You move lone pairs and pi bonds, right? Everything has to be a p orbital system. No breaks with sp3 hybridized things in the way, and always balance your charges, right? So the 4 rules, right? The 4 rules: don't change positions. You don't break sigma bonds. You only move pi bonds, so p orbital electrons and lone pairs. And what was the other one? The thing, balance charge. Yeah, balance charge. Right. So what's another way I can do here? I can move these electrons between 4 and 5. Right. That pi bond, those p orbital electrons.
Is the goal to make them all towards
Not necessarily. I'm just showing possibilities here. Right. Some of these are more important than others. Right. Some are better than others. How would you know? How would you rank resonance structures? What's something you should think about as far as understanding which ones are more important than others? It's not. We gotta let the charges go. My God, it's not about the charge. It's always about the octet rule. Let the charges go. Let it go. Make charges important again. Charge is nowhere near as important as the octet rule. The octet rule is the rule for above them all.
Why is this nitrogen staying positive?
Are any electrons moving away or towards it? No. So one of the nothing. When I move this arrow right here, did I do anything with this up here? No. So don't change any of it.
The first one.
The first one I did, but that has nothing. But this has nothing to do. This arrow right here has nothing to do with this.
But that one's still positive in the first one you did. That's what I'm kind of like.
Well, yeah, because I moved these electrons.
You're moving it towards it.
Yep, and then moved. The oxygens have a negative charge. How many bonds does nitrogen end up with still? It still has 1, 2, 3, 4. So it still has a plus charge.
So you like move things towards it and then you move things away.
Right, so these are the same, right? This oxygen having a negative charge here, right? It's not, these are basically the same, right? So it's not, I'm still moving electrons, but I just have the negative charge somewhere else. Right, so here, as I move this pi bond, where's the plus charge going to be at now? On 5. So one of the keys for resonance structures I like to think about is the part that doesn't change. Make sure you just draw that part first, and make sure you draw it correctly. Right? This whole part of this structure never changed, right? Just redraw that right away. Right? If it's not, that's one of the most common mistakes people make is they'll redraw this part, which has nothing to do with this arrow, incorrectly. Right? So make sure you draw the part that's not changing correctly right away. Okay. Is there another resonance structure we could draw?
I have a question on this one.
Sure. So the number of arrows, right? The number of arrows is not right. It has nothing to like. There's no saying like if you move 1, it's a good resonance structure. If you move 2, it's not. There's different ways to do this.
So like for one of the top ones, we could have just moved one set.
No, you couldn't. For one of the top ones, you couldn't just move 1 because then the nitrogen would have how many bonds? It would have 5. In which case, it would then break the rule of them all, the octet rule. So you always got to try to maintain the octet rule as much as you can. Now these ones, notice these ones. Do these guys maintain the octet rule? What have you made here? In these 2 examples down here, what have you made? Carbocations. Do carbocations have a full octet? No. So these resonance structures, do you think are they the most important ones? No, but they tell us something about this molecule, right? They tell us that carbon 3 and carbon 5 are electrophilic, right? They're electron deficient. Whereas if I look at this, do I know that right off the bat? Do I see that? No, right? As a matter of fact, this is an MCAT question. I just talked to somebody about this. This is an exact question from the MCAT about acids and bases, but basically it's about resonance structures with a nitro group, this exact kind of thing. Yes. Right, so what's another resonance structure? What's another resonance structure we could do? We can move the bond between 1 and 6. And so now the plus charge would be on carbon. So I'm going to draw in what I know hasn't changed.
The plus charge goes on the one that the pi bond that you move.
Right, who lost electrons.
So 6.
Right, so carbon 6 didn't lose electrons. 1 lost electrons, right? Who lost that? Carbon 6 still has that bond, right?
Oh,
All right.
okay.
So that's another resonance structure. So why are these important? Why does this matter? Because now I can look at this molecule in a different way. I could say, if I have a nucleophile, something that's electron rich, where might it go? It's not going to go to the nitrogen because the nitrogen already has a full octet. It might attack, right, or bond with carbon 3, 5, or 1. Right? So it tells me something how this molecule is going to react. So this is workshop number 1. Workshop number 1, second page.
Oh, that is nasty.
First one.
Yeah.
All right, so the first page we were identifying asymmetric centers, chiral centers, and now we need I added wedges and hatches, and you had to figure out R and S from here. So let's do this one first. So the first thing you need to do is actually draw in something. What do you need to draw in? Hydrogen. And what hydrogen needs to be hatched. And also be very careful, right? The wedge and the hatch have to be next to each other, right? You can't put the hatch up here. That wedge and the hatch have to be next to each other.
Would the wedge be carbon then?
Yep, so this is always implied. This is a carbon. Right? Don't have to draw it in, it's implied. Okay, so what's our lowest rank thing? Hydrogen, so we're going to call that green. And then we're going to go carbon, carbon, carbon. So that's a full-on tie. What is this carbon bonded to?
Two carbons and
An H. What is this carbon bonded to?
3 H's.
3 H's. What is this carbon bonded to? 3 carbons. So the red one is going to be this. The white is going to be this. And the blue is going to be this. So now you want to take your model, take one of them, just pick one. I would get the white and the red in the plane. White to your left, red to your right, and then see what's coming out at you. If it's blue, you're holding the right model. Okay, after much debate, this molecule, this center, that chiral center is S. Very good.
Yeah, you keep getting our ranking.
So now let's do, the ranking is the key. You gotta get the ranking correct. And then you gotta slow down and do red, white, and blue and figure out the right direction. You gotta slow down. So here, again, here's something that's hatched. So something else must be wedged then. And usually if it's not drawn in, it's a hydrogen. So the hydrogen must be wedged here. So let's do our rankings. Which one's gonna be the lowest? So that's gonna be green. And then again, we're down to this game. Carbon, carbon, carbon. That's a tie. This one is gonna be H, H, H.
What is the H at wedge?
What is this? That's just, it was the way I drew it in there. So remember, this is I actually put in the wedge and the hatch for the structure. Yep, I put the structure in that way. So for this carbon, what's that carbon bonded to? Is bonded to carbon, carbon, and carbon. What's this carbon bonded to right here? Oxygen, oxygen, oxygen. So this one wins. So this is going to be red. Then this would be white, and this would be blue. All right, take a second and see if you get that one, red, white, blue, see what RS. So to wrap up this one, this is a S stereocenter as well. So they're both S.